Hello, Algebra 2 CP students. Hopefully you're having a great day so far. Today, I would like to show you how to convert between forms of quadratic functions. Now that I feel like we have a really good grasp on how to graph quadratic functions in vertex form and graph quadratic functions in standard form, what we can do now is we can take a quadratic function that's written in vertex form and write its equivalent function in standard form, the equivalent representation. Likewise, we can take a quadratic function in standard form and come up with an equivalent representation of that function in vertex form. In other words, in like simpler terms, take something in vertex form and write it in standard form, and take something in standard form and write it in vertex form. Both processes are important to know. You will certainly be assessed on them on a progress and summative assessment. But both aren't really too complicated, and I think we can definitely knock out both of them in this one lesson today. So let's do vertex to standard first, and then we'll do standard to vertex second. Remember, just as a little refresher, so I'll put this over here, a little recall, that the vertex form of a quadratic function is written as f of x is equal to a times x minus h squared plus k. And remember, this is your stretch, the a value. This is your horizontal shift, the h. And this k is your vertical shift. And from this information, you actually get that the vertex of anything written in vertex form is h comma k, right? It's the horizontal shift comma the vertical shift. Right? So that's why it's called vertex form, because we can just kind of look at the function, extract the vertex right away, and move into creating our chart. All right. Standard form looks like this. We'd say f of x equals ax squared plus bx plus c. That's more what we saw when we were solving equations. Doesn't mean we can't graph them if they look like that, but typically that's more for algebra purposes. We see something written that way. But regardless, we can still find the vertex of something in standard form by doing negative b over 2a, and then taking that value and plugging it back into the function to get its matching y-coordinate. In other words, f of negative b over 2a. All right, and again, just like it was in vertex form, this a value is the stretch. Okay? So we have our vertex form and we have our standard form. Like I said, we're going to look at today how to take something in standard form and put it in vertex form, and likewise take something in vertex form and put it in standard form. Let's do vertex to standard first, because I think that's the easier one. All right, so taking something in vertex form and converting it to standard form. Suppose we have an example like this. F of x is equal to negative 2 times x plus 3 squared plus 5. And I want to take that function and rewrite that function in standard form as opposed to vertex form. Well, what we can do in order to accomplish that is really just expand the binomial. Here I have x plus 3 squared. What we can do is we can say, wait a minute, we know how that works. That's the same as saying it's x plus 3 multiplied by itself. And rewrite this as negative 2 times x plus 3 times x plus 3 plus 5. So what we can really do here is we can expand the squared binomial. And now that we have that, we can distribute, use our distributive property, combine like terms, and just rearrange such that it looks like it's in standard form. So take a look. We're going to get here, this is negative 2 times, let's do some first, outer, inner, last distributive property. We get x squared plus 3x plus 3x. See how the outer multiplication would be plus 3x? The inner multiplication would be plus 3x, so I'll skip to say plus 6x. And then 3 and 3 plus 9. Plus 5. Let's take that negative 2 coefficient all the way on the outside of the parentheses and distribute it everywhere. We're going to get negative 2x squared minus 12x minus 18. And then our lingering plus 5 is here. And lastly, we can just combine these like terms at the end and say that this is negative 2x squared minus 12x, and negative 18 plus 5 minus 13. And now, if you take a look, our function is written equivalently in standard form. These functions are exactly the same. I'll say f of x equals, just written in different ways. So if you sketch the graph of this, negative 2 times x plus 3 squared plus 5, and you sketch the graph of this, negative 2x squared minus 12x minus 13, they will be the same parabola. And that's, by the way, a great way to check and see if you actually did convert correctly. You could graph this, or maybe not do it by hand, but use something like Desmos or a graphing tool, like a graphing calculator. See if the graph of this is the same as the graph of this. And if so, then that's great. And if not, then maybe you made a mistake somewhere. But really, it's a matter of just multiplying out that squared binomial. Okie dokie. Let's take a look at another one, vertex to standard, and then we'll go from standard to vertex. Okay, here we go. One more example of this. If I had f of x is equal to negative 3 times x minus 1 squared plus 7. Okay, there's this typical vertex form problem, something that you may have even graphed on a practice worksheet or something like that. We could take that problem and rewrite it in standard form. I would say here, let's distribute that squared binomial. We could rewrite this as negative 3 times x minus 1 squared is x minus 1 multiplied by itself. X minus 1 times x minus 1 plus 7. Distribute those terms. We're going to get here, this is negative 3 times x, x squared. X times negative 1 minus 1x. Another minus 1x from the inner multiplication becomes minus 2x. And then minus 1 times minus 1 is positive 1 plus 7. Let's distribute that negative 3 now. That's hovering on the outside of everything. Negative 3 times x squared is negative 3x squared. Negative 3 times negative 2x plus 6x. Negative 3 times 1 minus 3. And then plus 7 is lingering on the outside there. And then lastly, we'll combine those like terms to say this is negative 3x squared plus 6x plus 4. And there we go. We've now converted our vertex form equation into a standard form equation, which is pretty cool. All right. Any questions about that? Hopefully it's sitting in your mind. Hopefully you're thinking about it. Hopefully it's lingering. Makes sense. Now, again, just in case you don't believe me, I'd be happy to show you the fact that these are, in fact, the same graphs. If I switch over to here, take a look. We have our first function we did was negative 2 times x plus 3 squared plus 5. Exactly as we expect, it would have a vertex at negative 3 comma 5 because that would be your horizontal shift comma vertical shift. And it is downwards facing because the stretch is negative 2. If I graph the function negative 2x squared minus 12x minus 13, same thing, which is pretty exciting. If I look over here, do the same thing with the other function, we got negative 3 times x minus 1 squared plus 7. And I graph that same function here, negative 3x squared plus 6x plus 4. Bam. They exactly overlap, the exact same function. And notice with this second one, by the way, vertex at 1 comma 7 exactly is what we expect it to be. Same thing here. Okay? So just showing you that these are, in fact, the same function. All right, going back over here. Let's get back to our notes. Let's do the other way around. Let's go standard form to vertex form. And in fact, what I'm going to do is use these exact two examples and show you that we can go backwards as well. All right? So starting with this first one, we'll do negative 2x squared minus 12x minus 13. Ready? This is now standard to vertex. All right? If I wanted to go from standard form to vertex form, take a look at what I could do. Starting with, again, the same example, negative 2x squared minus 12x minus 13. Right? What I could do is I can say to myself, well, remember, vertex form looks like this. F of x equals a times x minus h squared plus k. Okay, and we could try to fill in those pieces of vertex form from our standard form equation. One of the convenient things about vertex form and standard form is that this A and this A are exactly the same, right? The A in standard form is the same as the A in vertex form. That's why it's called A in vertex form. So the fact that A in our function here is -2 means that our vertex form A is going to be -2. So far we filled in this much. Right. Now, the only pieces we really have left to fill in are H and K. And you might think to yourself, well, hold on. H and K, those dictate the vertex of the equation. And if I find the x-coordinate of the vertex, we could potentially get H. And if I find the y-coordinate of the vertex, we could use that to get K. And that's absolutely true, because those transformations, H being the horizontal shift, K being the vertical shift, dictate where the vertex is. If I find the vertex, then we can fill in the value for H and K. How do I find the vertex of something in standard form? Well, we do that by our good old -b/2a, and then take that and plug it back in. So that's exactly what I would do here. I'd say the x-coordinate of the vertex is -b/2a, which is going to be the opposite of -12 over 2a, 2 times -2. So that's going to be +12 over -4, which is -3. Exactly what we saw before, you may remember. And so if I see that the x-coordinate of the vertex is -3, then H is, well, then this would go into here for H, and we see that this has to become a +3. In order to make the x-coordinate of the vertex be -3, this would have to be written as x plus 3, right? Because it's always the opposite. You could even see that, like, if you literally took -3 and plugged it in, what would it look like? It's going to say x plus 3, because it would be x minus -3. So far we've now filled in this much. And then lastly, to get that K, we just need to find the y-coordinate of the vertex. So how do we do that? We take -3, we plug it back in. We say f of -3 is -2 times -3 squared minus 12 times -3 minus 13. So that's going to be, let's see, -2 times 9 plus 12 times -3, 36 minus 13. And let's see what we get. This is going to be -18 plus 36 is +18 minus 13 is 5. And so since we get that our y-coordinate of the vertex is 5, that has to be our K value. That has to be our vertical shift. And we would therefore say that our function is -2 times x plus 3 squared plus 5, which, if you notice, is exactly what it was at the start. All right? So I like this because it really is a good revisiting of the idea of transformations. The fact that the horizontal shift and vertical shift of something in vertex form are used to find the vertex. And the same can happen in reverse. If I know what the vertex is, then I can use those to find my horizontal shift and vertical shift. Okay? One thing that I should note for the sake of noting it is there is another way to go from standard form to vertex form, and that can be done by completing the square. I know that brings back some PTSD for some people. Completing the square on this quadratic. And if you complete the square, remember, you'd eventually end up with that squared binomial, and you could rearrange terms to make that occur. That is definitely a great way to convert back as well. It's a good review of completing the square way back when. I typically would show that off with an Algebra 2 honors group for sure. But I think for Algebra 2 CP, this really helps to hammer home that concept of the transformations, the horizontal shift and vertical shift, and it kind of puts it all together in a nice bow. So if you're interested in seeing the alternative approach to convert from standard form to vertex form by completing the square, please reach out to me via email. You see my email in the video right over there on that side down there. I'm trying to point to it. Please make sure you reach out to me via email, and I'll be happy to show that off to you anytime. All right, right over here. Okay, great. Now, let's go ahead and try one more problem, and then we'll call it a day. All right, we'll call it a day. Ready? Second example. let's convert right back to where we were. We had negative 3x squared plus 6x plus 4. Let's get it back to what it was. Negative 3x squared plus 6x plus 4. There's our standard form equation. If we want to get it to vertex form, well, again, I'm just kind of like filling in the missing pieces of the puzzle. You can think of it that way, right? This A in vertex form is the same as this A in standard form, both of which are called the same thing because they both represent the stretch. And so we'd be able to fill in that piece of the puzzle to say we currently have negative 3 times x minus h squared plus k. And I can fill in h and k now, the horizontal shift and vertical shift, by finding the vertex. So let's make that happen. I would say that the x-coordinate of my vertex is, let's see, negative b over 2a, which is going to be negative 6 over 2 times negative 3, which is negative 6 divided by negative 6, which is positive 1 itself, right, which is great. Now to find the matching y-coordinate, I could take that value, that 1, plug it into my function, and get that this is negative 3 times 1 squared plus 6 times 1 plus 4. What does that come out to be? Let's see, negative 3 times 1 squared, that's 1 squared is 1 times negative 3 is negative 3, plus 6 is positive 3, plus 4 is positive 7. And so notice I'd fill in the pieces. I'd say, oh, my x-coordinate of the vertex is 1. That would have to go in for my horizontal shift and make this look like negative 3 times x minus 1 squared plus k, because x minus 1 would have x-coordinate of the vertex at positive 1, and you're literally taking this and plugging it in for your h. And then 7, well, that being the y-coordinate of my vertex, means that would have to go in for k. F of x is equal to negative 3 times x minus 1 squared plus 7. We've now filled in all of the pieces of my puzzle here, and we're done. We've converted back to vertex form. Okay? And that's that. So, just a quick little recap. We can convert from vertex form to standard form by expanding the squared binomials. Just a little bit of algebra. Take what you see here, multiply it out, combine all the like terms. A great exercise in doing that, by the way. Nice little algebra review. To convert from standard form to vertex form, it ties in what we know about the transformations to say the stretch is the same, and the x-coordinate of the vertex corresponds with the horizontal shift, the y-coordinate of the vertex corresponds with the vertical shift. And just using that relationship to build our vertex form function, to fill in the missing pieces. All right? Hopefully that made sense. We will practice a little bit later this week before we have a progress assessment next week, and then gear up for our summative soon after. All right? We are going to learn something new tomorrow. So again, it's going to be sort of this concept and the concept we learned tomorrow. We're going to combine them into practice for the rest of the week, and they're going to be on your progress assessment next week. Study hard, do your very best. If this didn't make sense, please come with questions next class, and I'll be happy to go through them together with you. But other than that, I hope you have a fantastic rest of your day. Thank you for your attention and focus today, and I'll see you next time. Take care, everyone.